Uh,
Uh,
it's being recorded.
Perfect. Hello, everyone. Welcome to another session of the TBS Colloquia. Today, we have the pleasure of having James Freeburn with us. He's a PhD student at Swinburne University, working with Chef Cook and Anna Smoller. And he will tell us all about gamma ray bursts of orphan afterglows. So please, James, take it away.
Yeah, thanks, Priscilla. So as Priscilla said, I'm a student at Swinburne in Australia. I'm primarily interested in gamma ray bursts and their afterglows. I do some work in gravitational wave follow-up, and I'm just kind of interested in doing like high cadence optical imaging of interesting objects just in general. But for this talk, I'll primarily be talking about the paper that I just published recently, which is centered around um, like an untargeted search for gamma ray burst orphan afterglows. So these are afterglows that don't have an associated gamma ray burst. So we did this search using the Deep Wider Faster program, which has some really unique data from the dark energy camera. Um, and we managed to find some interesting transients, but unfortunately, none of them were these orphan afterglows. Um, but using kind of this non-detection, we can say some interesting stuff about gamma ray burst jets and their geometry. So I'll just kind of explain what gamma ray bursts are. So they were first detected in the 1960s by a US military satellite, which was actually designed to look for nuclear detonations from the Russians. But they kind of serendipitously found these sources of gamma ray emission coming from the opposite directions where they're expecting. So out into the universe. And at the time, they kind of knew that there were these kind of short bursts of radiation, and they were coming from cosmological distances. So they were extragalactic sources. And this made them some of the most energetic uh, events in the universe. But over the last few decades, we've kind of built up the story of what's happening with these events. So they primarily happen in one of two ways. The first way is a compact binary merger between two neutron stars, or a core collapse supernova. So in this, for the Orphan Afterglows project, we're primarily worried about the core collapse supernova scenario. But in either case, you get a central and like compact object, which accretes material from the progenitor event, which then projects this relativistic outflow. And then in the outflow, you have internal shocks colliding, and that's where your prompt gamma ray emission comes from. But as it kind of continues traveling into the interstellar medium, it interacts. Um, it interacts and kind of decelerates, and the synchrotron emission associated with that is what we call the afterglow, and that's bright in X-rays all the way down to radio. Um, so why do we care about gamma ray bursts? So we care about them because we can use them as tools to understand the universe. So they can be used for cosmology. So with the merger scenario, you can use them to study the local universe by measuring the Hubble constant. But you can actually use long GRBs to study the distant universe, to constrain things like star formation. They're very extreme events, so you can use them to study fundamental physics. And particularly in the merger scenario, they're the sites of nuclear synthesis. When baroneutron star mergers happen, you get what's called a kilonova, which is where most of the heavy elements in the universe are created. But even apart from using them as tools, they're actually interesting objects in and of themselves, and we still don't know quite a lot about them. So we really don't fully understand how the jet launching mechanism works, or how exactly the GRB emission mechanism works either. And we also don't know fully how much energy is released intrinsically in these events, or how often they occur in the universe. And a lot of these, even so, using them as tools or understanding them fully, we really need to understand the jet's geometry and kind of how wide or narrow it is. So this is where this project kind of comes in. But we kind of traditionally model GRB jets with the top hat model. And that's where you have a basically uniform energy distribution out to an angle, the jet's half opening angle, and we have a viewing angle that's inside that. So we're on axis from the event. And actually, if we use this model, we can predict a lot of the phenomenon or phenomena that we see in the afterglow. So this is a light curve from a GRB that happened in 1999. And you see this kind of, so it's just brightness over time. And you see this break in the light curve at about a day post-burst. And that's what we call the jet break. And it essentially marks the jet transitioning from a relativistic regime to a sub-relativistic regime. So it's slowing down and spreading out. And this is very well predicted by the top hat model. So we're sitting good with this model so far. But we know that this isn't the full story. So as the jet kind of pierces through the stellar material from the progenitor, you're going to get mixing. And this is a hydrodynamic simulation that was done. And you can see that it's definitely not a uniform distribution of material. There's kind of this interface between like the energetic core and the outside space. And so if we're thinking about this, we might want to adopt a more complex model. So one of the ways we can do this is with the structured jet model. And that's where you kind of assume a uniform core and then a gradual decay out to the edges. And actually with GRB 221009A, which was the brightest GRB ever detected, it gave us really unprecedented signal to noise. And particularly with the X-ray afterglow, it meant we can monitor it for a really long time with really high precision. So this is the light curve of the X-ray afterglow. So it's just, again, brightness over time. And you see, what you don't see is the jet break that I showed in a previous slide. So that's kind of inconsistent with the top hat model, but can be explained by a more complex jet model, such as a structured jet. And these authors last year were actually able to measure some of the jet geometry with 221009A, and they found that the core of the jet was very, very narrow at about 1.2 degrees compared to the full jet opening angle. And what's even weirder is our viewing angle was very close to on axis from the core of the jet. And this is kind of an unexpected result because if you kind of consider the geometry of what's happening, you would be way more likely to see the afterglow at a large viewing angle than a small viewing angle. So we kind of need to explain why we saw this event at such a small viewing angle. And one of the ways we can explain it is if we restrict the gamma ray emission to the core. So if we do this, the reason why we don't see other events like it at larger viewing angles is because we don't see the GRB emission, so we don't trigger on it, so we don't see anything, basically. But in this scenario, you would actually get afterglow emission emitted out to the entire jet opening angle. And so if you're off axis from the core, but on axis from the jet, you would see an afterglow without associated GRB emission, and that's what we would call an orphan afterglow. So for this search, I've been using the Deeper, Wider, Faster program. So data from the Deeper, Wider, Faster program, rather. So this is a transient survey that is designed to look for fast transients in multiple wavelengths, particularly FRBs. So we have like simultaneous wavelength coverage from radio all the way up to X-ray. But I'm primarily worried about the DECam observations that are used in the DWF program. And the DECam observations are really unique amongst transient surveys. So we use 20-second exposures, which corresponds to about a minute cadence, so taking images every minute. And because DECam, it's mounted on a 4-meter telescope, it's a very powerful instrument with a really wide field of view. We get pretty good depth at a wide field with a really, really high cadence compared to other surveys here. And this kind of allows us to probe a parameter space that isn't probed by other transient surveys. And this is really important for a search for orphan afterglows, because afterglows are very fast evolving events. So here is just kind of an example of a typical afterglow light curve you might see. And you can see that it fades about 7 magnitudes in 24 hours, which is really, really fast. So you can imagine with a day cadence, you're kind of missing a lot of the times while the afterglow is bright. And by sampling every minute, you're kind of allowing yourself to probe the afterglow while it's at its brightest. And so what this actually allows us to do is probe deeper into the universe and get a larger volume. So this is why it's kind of an interesting new avenue to look for orphan afterglows, because it's kind of a different parameter space than other transient surveys are looking. So the data I've been looking at for this project is about 100 nights of this data, which is about 10 million light curves, and it corresponds to about 50 gigabytes of just raw photometric data, which is quite a lot. And you can imagine we have to get pretty creative in how we're gonna search all of this data. So kind of the main two things that we need to do is figure out how many afterglows we would expect to see, given some assumptions about the jet structure, and then actually figure out how we're gonna look through all this data to identify candidates. So just focusing on how we're going to find them, I used this population synthesis model that was developed by Galando et al. In 2013. And so this is a plot of the fluence of a GRB. It's kind of a proxy for its energy versus the peak energy of the GRB spectrum. So the black squares in this plot are Swift detected gamma ray bursts. So Swift is a gamma ray burst satellite in orbit, and it detects a gamma ray burst every few days. And the red contour lines are the predictions from this population synthesis model of how many we should see with Swift. And you can see there's pretty good agreement between the model and our observations. And actually, if you apply kind of the output from this population synthesis model to afterglows, you actually get good agreement with observations as well. And so that's really important for this search because we're looking for afterglows. So what I did to kind of understand exactly how many we're expecting to see and our efficiencies is I injected these afterglow. So I used the population synthesis model to predict afterglow models, which are then injected into the DECam data that we're using for the search. And you can see this is one of the light curves, one of the injected light curves that we get. And so this is the kind of evolution that we're expecting to see. And actually, with these injected afterglows, it makes it very easy to do things like understand how efficiently we're recovering orphan afterglows from this population. And don't worry too much about the different kind of colors in the plot, but you can see that we kind of get a pretty complete sample up to about magnitude 20 for the peak magnitude of the afterglow. So yeah, so that in the light curve where it peaks and then fades away. Yeah. And so using like these efficiency calculations in the population, how many should we actually see in the DWF data? So for the jet model, this is kind of a little toy plot of our model. And so you see our uniform kind of energy distribution out to an angle of theta c. So that's the core of the jet, and then a power law decay out to the jet opening angle, which is denoted by theta w. And then the power law index. So basically the steepness of the decay is given by B. And so in this plot, we're kind of showing the power law index, so how steeply the energy distribution is dropping off versus the geometry of the jet. So basically how wide the afterglow emitting region is compared to the gamma ray emitting region, which is theta c. And so at the top left, you're kind of approaching, so it's a very shallow power law index and a very wide jet structure. So that's almost like approaching an isotropic distribution, which is probably not something that's super realistic. But then down at the bottom, you're looking at more of a top hat kind of structure. And with the isotropic, going towards more isotropic, I guess, jet models, you're predicting more and more afterglows, which is kind of what we expect. And then with top hats, you're basically going to see zero. but we can kind of, you can see how we can kind of constrain with this search, we can kind of constrain what jet models are possible versus not possible, or favor different ones over the others. So now we're kind of going into how exactly I did this search. And that involved the use of a machine learning classifier. So for the training data, we used those injected afterglow models I showed in a previous plot, and then we kind of parameterized them first with the power law fit to the fade of the light curve, and then in conjunction with some other kind of summary statistics of each light curve. And then I trained an classifier using XGBoost to kind of distinguish between these afterglow light curves versus basically everything else in the DWF data. And then at the end of this process, we got about 30,000 candidates. And then after removing image artifacts and cross-matching with catalogs to remove like stellar sources, we ended up with 51 candidates. So I mentioned before that we cross-match with catalogs, but actually because DWF, we're using DECam and it's a powerful instrument, we're actually reaching deeper than a lot of other catalogs go, particularly Gaia. So Gaia can give you parallax measurements, which can help you understand or identify which sources are in our galaxy versus extragalactic sources. And we don't care about the ones in our galaxy, so we can remove them. But because we're reaching deeper than Gaia goes, we're still getting a lot of these stellar sources remaining. So we're having to kind of get creative in how we can remove stellar sources from our candidates. So flare stars primarily come from M dwarfs, so low mass red stars. And when we're looking for orphan afterglows, we're probably going to see something like this. So this is a candidate that we found in the data using our machine learning classifier. And you can see that this is something we would expect if it was an orphan afterglow. We see this kind of blue, kind of blobby thing. It's not a very technical word, but it's not. The point is, it's not a point source. It's kind of extended and it's blue, which kind of indicates star formation, which is where we expect long GRBs to occur. But this is actually what we saw. So this looks very much like a point source, and it's very red. So this is something that's very reminiscent of an M dwarf, which would indicate that it's probably a flare star. And we can quantify this using this set of plots. So here, these are called color plots. So you're basically just plotting the difference between two filters of these coincident sources against another difference between two filters. And you can see this gray region, that's the main sequence. And then going up to these like orange boxy bits, those are where we'd expect M dwarfs to lie in our color plots. And these orange kind of points in these plots are sources that have colors that are consistent with an M dwarf. So we can kind of rule them out as probably flare stars. Some of these blue ones lie along the main sequence, so you can rule them out because they're probably they're not M dwarfs, but flares can still occur in higher mass stars. So they're probably galactic anyway, and definitely not afterglows, so we can rule them out. The green ones, there's actually not enough archival information. They're too faint to kind of determine whether or not they're M dwarfs, but they're still consistent with the M dwarf explanation. So they're probably not orphan afterglows. But what's interesting is candidate 47 on the plot. You can see it's kind of bouncing around weirdly in these plots and not lying where you would expect an M dwarf to lie. And actually, this candidate has a really beautiful light curve. You can see this nice rise and fade. And this is its coincident source. So again, it's not something that we would expect from an orphan afterglow. It's not, it looks very much like a point source, and it's not blue like we would expect. So we can be pretty confident that this, while we don't know exactly what it is probably not an orphan afterglow. So we can say pretty safely, okay, we haven't found any in the data. So looking back to that plot I showed earlier, what can we say then about the jet structure? And so, yeah, I'm kind of repeating that plot before, but instead of the expected rates, it's the probability of each kind of jet structure scenario based on the fact that we have achieved a non-detection in the DWF data. And you can see that kind of as expected, we're favoring something towards a more top hat jet model over a wider, shallower kind of jet structure. So just to summarize the projects, we haven't found any orphan afterglows yet, but we've got some really interesting constraints on GRB jet geometry. And so looking forward to other surveys that could do stuff like this, and I guess I'm in the transients and variable stars for LSST, so I'll talk about LSST. So this is a plot of something, of a light curve that you would expect from a afterglow, and kind of plotted with those dotted lines are the different limiting magnitudes for each visit that you would get with LSST. And then the kind of wide, fast, deep main survey has a cadence between 2 and 5 days. And really with this cadence, it's going to be very difficult to identify afterglows at all. You'll basically get somewhere between 0 detections and maybe 2. So that's not looking great. But for some of the fields I'm reading, it might be outdated, but I read it today. There's going to be a 5-hour repeat visit. So you get one image and then 5 hours later, you get a repeat visit. And this would actually be a really good way to identify candidates. But really, we need like supplementary observations to actually like fully identify afterglows in the LSST data. So this would kind of involve either targeted follow-up, so getting candidates from the LSST wide, fast, deep survey, and then following up those specific candidates, or you could have like an accompanying survey that like matches the pointings that LSST is doing, but just doing it with a higher cadence. So I think there is really good opportunities with LSST to do searches for these kind of orphan afterglows. So It's really exciting stuff. But um, another survey that could work for searches like this is TESS. So TESS is the Transiting Exoplanet Survey Satellite. I got it. And so it's designed to look for exoplanets, but actually, at the moment, it has like a 2 minute cadence with a massive field of view. It's not as deep, it's nowhere near as deep as LSST or DECam, but it has like almost continuous, uh, it's almost continuously observing the sky. So it could be a very powerful way of probing orphan afterglows. And actually, you could even use Tess and Ruben in conjunction with each other, and might be able to get some interesting results that way. So I'll kind of move on to my next project. So we're moving away now from orphan afterglows and just going to normal. Well, I shouldn't say normal, but kind of your typical scenario with GRBs where you have targeted follow-up to a GRB event. And one of the main kind of mysteries with GRBs at the moment is tying them to specific progenitor scenarios. So, as I said before, you can either have a compact binary merger or a core collapse supernova. And then in the case of a compact binary merger, you have kind of the material from the neutron stars decaying, and the thermal emission from that is your kilonova. And then with a supernova, with the core collapse supernova scenario, obviously you'd have your supernova emission. The problem is GRBs are very bright, and their afterglows are very bright, and we're often detecting them at very in the distant universe. And kilonovae and supernovae are comparatively quite dim. So it's often very difficult to actually get detections of these kilonovae or supernovae associated with these events. So we're a little bit stabbing in the dark when we're looking at GRBs and trying to tie them to progenitors. So typically, what has happened is you look at the duration. So in this plot, you have, oh, where's my cursor? There it is. You have T90, which is basically duration, versus E peak, which is the peak energy of the GRB spectrum. And you see these two distributions, and you say, okay, these blue ones over here, so the longer duration, lower energy GRBs are your collapsars, so the core collapse coming from core collapse supernovae, and then the shorter duration with higher energy emission, those are coming from your binary neutron star mergers. But actually, we found in recent years, so this plot is a little bit outdated. It was from a paper in 2021. But in recent years, there's been a few detections of kilonovae, so what you would expect from a binary neutron star, associated with a long GRB. And you can see, even apart from that, these two distributions are overlapping a lot. So with any one detection, it's very hard to tell exactly what's going on. And with this GRB I'm currently working on, which is 2210, oh, 2210, 220831A, it kind of sits in the interface between these two distributions. So this is kind of an area where we really want to understand what's going on with the progenitor. And so looking at the afterglow light curve, which is very nicely sampled. So we followed it up with the deep wider fast program with some DECam observations, And there was a few collaborators who got some VLT observations and some Gemini. We were able to kind of sample the light curve really nicely. And there's also a radio detection with the Australia Telescope Compact Array, and a detection, or I guess a low significance detection in X-rays as well. So it's a very kind of rich data set spanning like the entire electromagnetic spectrum, which is pretty cool. But is there anything we can kind of tell from the afterglow to give us any hints of what the progenitor of this event is? So the fit I showed in the last slide kind of indicated that there's a low density environment around the GRB, which is actually typical of a short GRB or a binary neutron star merger. So that could be a hint towards the BNS scenario. And then kind of a interesting thing about the light curve as well is the post-break power law index is very steep. And it's a kind of a strange result. It's basically too steep that can be fit by afterglow models. So that's quite mysterious, and that's something we're kind of still thinking about. Another kind of hint we can look at of what the progenitor scenario is by looking for the host galaxy. So BNS events generally occur at lower redshift, and collapsars generally we see them at higher redshift. And we actually got a Gemini program to do follow-up to this GRB to try and detect its host galaxy, and we didn't find anything. So this might, you could say, okay, we didn't find anything, so maybe it's a collapsar occurring at high redshift, and it's just too faint for us to see. But actually, with a lot of short GRBs, you can get very large angular offsets between the event and its host galaxy. And so we kind of did a search in the nearby sky to look for any galaxies that have a high kind of chance alignment significance. And we didn't find any galaxies that kind of were significantly associated with our GRB. So this is kind of indicating more towards the collapsar scenario, so a high redshift galaxy. But again, it's hard to say because you can have a low chance significance, but that doesn't necessarily mean that that you haven't found the host. The host galaxy isn't there. It's just hard to say whether or not it is the host galaxy. So just to summarize the work on this GRB is we basically don't understand what's going on with the progenitor, and there's some really kind of strange stuff happening with the afterglow light curve, and there's no conclusive detection of a host galaxy, but there are some HST observations planned to really get deep and understand what's going on with it. And I'll be preparing a paper in the next few months talking about it. So stay tuned for that. But yeah, that's basically it for my talk. So I'm happy to take questions.
Thank you so much, Shim, for this great presentation.